In this example, I'm going to analyze an inelastic collision. And if you remember what an inelastic collision is, it's a collision where the kinetic energy is not conserved. In other words, there's more kinetic energy before than after. So this may be due because of the two objects crumple and there's some energy loss during the crumpling. But in a nutshell, the kinetic energy before and afterwards are not the same. So I'm also going to throw a little twist in here with two cars approaching one another. So in this example, I'm going to have a car that is traveling to the left and one to the right. So here's the ground here. I'm going to have this car traveling to the right, and I'm going to have another car approaching. So kind of a head-on collision. And we're going to see how we model velocities that are in opposite directions. Um, the mass of the first car, I'll call it M1, is going to be 5 kilograms. And it's initially traveling a velocity v1 initial with an I there. It's going to be traveling at 5 meters per second. This object over here, M2, is going to have a mass of 2 kilograms, and its initial velocity, v2 initial, is going to be, now velocity is a vector, so I'm going to say minus 2 meters per second. Positive values are to the right and negative values are to the left, just like the number line. If you had a number line right here with the x-axis, let's say in math class, anything over here is positive, anything past the origin the other way is negative. So they're going to collide, and we're going to analyze or look at the velocities after the collision. So after the collision, and even though there are two separate pictures here, this is an instant of time after. Uh, and I'm just drawing a spacing here so I can draw some arrows, but they're really very, very close to one another. The mass 1 is going to be traveling at a reduced speed of v2 final, I'll say, 3 meters per second because it's slowed down. And m2 over here is going to have a velocity, and we are going to find that velocity. How fast is the second object traveling after the collision? So head-on collision, as we're going to see later, energy is not going to be conserved, so it's an inelastic collision. So it's a 5-step process. So we define the positive direction. So as you can see, that was very important because we have velocity vectors that are now pointing in both directions. So I'm going to say this is the positive direction. That's step number 1. That's done. Step number 2, we're going to state the conservation of momentum. Conservation of momentum. This is the initial momentum here before the collision, and this is the momentum after the collision, and those momentum are equal. Next, we draw momentum buckets. So the little twist here is that we have one object traveling in the positive direction and one in the negative direction. So in the bucket model, what I do again is I go to each bucket, I visit each bucket, and I say what momentum does it have. So first object has momentum. I'll fill in that bucket here, and the little trick here is that this one has a negative velocity, so it's an upside down bucket to denote negative velocity or negative momentum. Momentum is also a vector because it depends on velocity. And then the first object after the collision is traveling forward, okay? And then the second object, my best guess at it's traveling forward as well, so it's a right side up bucket. So we use the same concept that we did with an elastic collision, where things travel in the same direction. So I write my momentum equation, mass times velocity, initial. And because this is upside down, there's a negative sign here. Note the negative sign, and that's because it's a negative velocity. So that's how we take care of negative velocities. Then I have object 1 after the collision, object 2 after the collision. So then I write my conservation of momentum equation, which is basically this equation right here. So I have m1 v1 initial plus m2, it's actually a minus m2 v2 initial, there's a minus sign there, equals m1 v1 final plus m2 v2 final. And so when I solve this, I get, if I plug in the correct numbers here, mass 1 is 5 kilograms. It's traveling a velocity of 5 meters per second before the collision. The second object has a mass of 2 kilograms and traveling 2 meters per second. The negative sign here again represents it's traveling to the left, or in the negative direction. After the collision, the 5 kilogram mass is traveling at a reduced speed of 3 meters per second, and the 2 kilogram mass has a new velocity, and I don't know, v2 final. Now I'm trying to solve for that variable. v2, I should say final here to be completely correct. So mathematically, this is what? 25 minus 4 equals 15 plus 2 v final, v2 final. So this is what? 21 equals 15 plus 2 v2 final. And this is 6, if I bring the 15 over here, equals 2 v2 final. Therefore, v2 final equals 3 meters per second. 3 meters per second. And box your answer. And I get a positive value, which is consistent with the fact that it goes to the right, because that's the positive value. Just to ensure that this is an inelastic collision, you could calculate the kinetic energy before and kinetic energy afterwards. So I'm not going to do it in this example just for time's sake, but I could go to each term, and you should probably do this just to verify. 1/2 m1 v1 squared and 1/2 m2 v2 initial squared, this initial as well. Add those guys up, and that should be not equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And if you do this calculation, you'll find that this is much more energy. According to my calculations, it's twice as much energy than before. And why this is because in this particular collision, there's a crumple zone, and when the two objects hit and they crumple, there's going to be some energy loss during the collision, some kinetic energy loss. So I don't conserve kinetic energy. That's unlike two billiard balls that are hitting, where they're going to be not deformed very much or at all, and so you maintain the same amount of kinetic energy before and after the collision. So that's an example of the bucket model for an inelastic collision.